We meet once again for two-phase flow with phase change in conventional and miniature channels. We have discussed two-phase flow models and how to calculate pressure gradients for two-phase flow using different models. Now, today we will discuss how to find the pressure drop in two-phase flow. Pressure drop in two-phase flow. So, first let us consider the homogeneous model and find the pressure drop using the homogeneous model. The pressure gradient by homogeneous model is given by this expression 1 upon 1 minus m square 2f upon d g square v bar plus g square v f g dx by dz plus g sin theta upon v bar, and here m square represents the compressibility of the vapor phase and it is equal to g square x absolute value of dVg by dP, and if m square is very small then we can neglect it, and then in that case the denominator becomes equal to 1, and then the pressure gradient becomes simply the quantity, the expression in the bracket, and the first term is identified as the pressure gradient due to friction, the second term is the pressure gradient due to acceleration, and the third term is pressure gradient due to gravity. This we have done before. Now, from pressure gradient, how do we find the pressure drop? The pressure drop is the decrease in pressure from one point to another point. Usually, in a pipe, we calculate the pressure drop in the pipe, that is from the inlet to the outlet of the pipe. Pressure gradient is calculated at a point. In a pipe, pressure gradient we can calculate at the inlet or at the outlet or at any point in between. In the numerical examples, we have calculated pressure gradient at the midpoint of the pipe, but we could have calculated at any other point, and in general we would have got different values of pressure gradient at different points. So, to calculate the pressure drop, we will have to integrate the pressure gradient from the inlet to the outlet of the pipe, and since in general it varies from point to point, the integral will not be simply the pressure gradient multiplied by the length. So, let us see how to do this integral. Consider pressure drop in an evaporator tube and assume that at the inlet it is saturated liquid. At the outlet, in general, it will be a two-phase mixture. So, the pressure drop will be equal to the pressure drop due to friction plus pressure drop due to acceleration plus pressure drop due to gravity. And here the pressure drop due to friction delta P f is the integral of the pressure gradient due to friction. With dP by dz we put a minus sign and then we integrate, and what we get is the decrease in the pressure. We usually calculate the decrease in pressure rather than increase in pressure, because usually there is decrease in pressure due to friction and due to gravity also, and many times due to acceleration also there is decrease in pressure. So, delta P f is integral 0 to L minus dP by dz f dz, and then we substitute the expression for the pressure gradient, and then V bar is equal to V f plus x V z x V f g. V f and x V f g we will be assuming to be constant, but x is not constant in an evaporator tube, it changes from point to point. At the inlet x is equal to 0, at the outlet we have the maximum value, and in between there are intermediate values. So, we will have to do an integral. So, delta P f is equal to integral 0 to L 2 f T p upon d g square V f 1 plus x V f g upon V f dz. Here we have taken V f common from the quantity in the brackets, so that within brackets the quantities are non-dimensional. Then we can convert from dz to dx in the integral, and therefore, instead of dz we write dz by dx into dx, and we will see shortly why we have done this, because it will be easier to do the integral with respect to x. Now, dp by dz A, the pressure gradient due to acceleration, is substituted in the expression for delta P A, and we get integral 0 to L g square V f g dx by dz. Here also we want to convert from the integral with respect to x. So, we cancel dz, and then we get g square V f g by V f dx, integral 0 to x naught. We will see later why we have written, instead of V f g we have written V f into V f g by V f. Then the pressure drop due to gravity is integral of the pressure gradient due to gravity, and it is equal to integral 0 to L g sin theta upon V bar dz, and then we substitute for V bar V f plus x V f g, and we take V f common. So, we get this integral, and then we convert from dz to dx. So, finally, we get integral 0 to x naught g sin theta upon V f in the bracket 1 plus x V f g by V f dz by dx. Here x naught is the quality at the outlet, at z equal to L, x is equal to x naught. Now, in order to do this integral, we will have to make some assumptions. If we do not make any assumptions, then we will have to do numerical integration. Also, we have assumed that m square is much less than 1. If m square is not negligible, then we will have to keep m square, and then all these pressure gradients will have to be multiplied by 1 upon 1 minus m square, and then we will have to do numerical integration, because m square contains x, and then we cannot take it out of the integral sign, and therefore, we will have to do numerical integration. So, here we want to solve it analytically and get a closed form expression. So, therefore, we are considering only those cases where m square is much less than 1, and further we are making some assumptions. So, we assume that FTP is constant over the length, and also VFG by VF is constant over the length. So, unless the pressure is low, the change in pressure or the pressure drop will not affect the properties very much, and therefore, VFG by VF will be nearly constant. And we also assume that dx by dz is equal to constant, and it is equal to x naught upon L. This comes from energy balance by assuming that the heat flux is uniform, and then by doing a simple energy balance we get dx by dz equal to constant. So, therefore, the quality varies linearly over length, and we get dx by dz is equal to xo upon L. So, we substitute in the expressions. Dz by dx will be equal to the reciprocal of dx by dz, and it will be L upon xo. So, after substituting, we get delta P f is equal to dz by dx will come out of the integral sign, because it is constant, and then we have integral of 0 to x naught 1 plus x V f g by V f dx. And after integration, we get 2 f t p L upon d g square V f bracket 1 plus x o by 2 V f g by V f. The pressure drop due to acceleration is g square V f g by V f 0 to x o dx integral. So, So, the integral will be just xo, and we get this expression g square Vf Vfg by Vf xo, and Vfg by Vf xo is denoted as R1. Okay. So, we can write delta P A as g square Vf R1. Later we will see that when we use the separated flow model, we get another expression which is called R2, and therefore, here this Vfg by Vf xo is called R1. The pressure drop due to gravity involves the integral of 0 to xo dx upon 1 plus x Vfg by Vf, and when we integrate, we get a logarithmic expression. Okay. So, finally, we get the pressure drop delta P equal to delta Pf plus delta Pa plus delta Pz, and delta Pf is equal to 2 FTP L upon d g square Vf bracket 1 plus xo by 2 Vfg by Vf. Delta Pa is equal to g square Vf Vfg by Vf xo, and delta Pz is equal to g sin theta L upon Vfg xo ln of 1 plus xo Vfg by Vf, and by adding these three terms we get the total pressure drop. So, this was for an evaporator tube. Now, let us consider a condenser tube. In the condenser tube, let us consider saturated liquid at the outlet. In the evaporator, we considered saturated liquid at the inlet. Here, let us consider that after condensing, we get saturated liquid at the outlet, and at the inlet, it is a two-phase mixture with a certain quality. Let us call it inlet quality Xi. So, again we assume FTP equal to constant and Vfg by Vf equal to constant, dx by dz will be constant by simple energy balance, and it will be equal to minus Xi by L. M square we have already assumed to be negligible. So, now we can do the integration, and in the frictional pressure drop we get the integral of Xi to 0 1 plus x Vfg by Vf dx, and after integration we get the final expression as 2 FTP L by d g square Vf 1 plus Xi by 2 Vfg by Vf. The pressure gradient due to acceleration is also similar to the case of evaporator, except that in this case the quality gradient is negative. So, therefore, we get a minus sign and we get g square Vf Vfg by Vf Xi. The pressure gradient pressure drop due to gravity is also similar to that for the case of evaporator, and we get the integral of Xi to 0 dx upon 1 plus x Vfg by Vf, and after integration we get a logarithmic expression. So, finally, we get the pressure drop as delta Pf plus delta Pa plus delta Pz, where delta Pf is equal to 2 FTP L by d g square Vf 1 plus Xi by 2 Vfg by Vf, delta Pa is equal to g square Vf Vfg by Vf Xi. This should be Xi, here also Xi, and here also Xi. Okay. So, the pressure drop due to acceleration is negative in this case. That means there is pressure rise due to acceleration. Okay. Due to friction, there is always pressure drop, because friction always opposes motion, relative motion, and due to acceleration, in this case it is actually deceleration rather than acceleration, and therefore there is pressure rise due to that. Due to gravity, whether there is pressure rise or pressure drop, or whether delta Pz is 0, it will depend on whether the tube is horizontal or vertically upward flow, downward flow, or inclined upward or inclined downward. Okay, it will depend on theta. So, the total pressure drop we can get by adding all these terms. This is also xi. Okay. So, we have considered pressure drop in a evaporator tube and a condenser tube. Now, let us consider two-phase flow in an adiabatic pipe. So, in an adiabatic pipe, there will be no change in quality, because we are neither heating it nor cooling it. There can be change in quality due to higher order effects, which we are not considering right now. So, here we will assume that the quality is constant, and then we also assume FTP equal to constant and VFG by VF equal to constant. So, the frictional pressure drop is equal to the integral of the frictional pressure gradient, and here we see that everything comes out of the integral sign, and we are left with only the integral of 0 to L dz, which is nothing but the length of the tube L. So, we get delta Pf as 2 FTP L by d g square Vf in the bracket 1 plus x Vfg by Vf. The acceleration pressure drop will be equal to 0, because the acceleration pressure gradient is 0, there is no acceleration, no deceleration. So, delta Pa is equal to 0. The gravitational pressure drop is equal to the integral of the gravitational pressure gradient, and everything comes out of the integral sign, and we have only 0 to L integral dz, which is equal to L. So, we get delta Pz equal to g sin theta L upon Vf 1 plus x Vfg by Vf. So, we have delta P equal to delta Pf plus delta Pa plus delta Pz, and delta Pf is equal to 2 FTP L by d g square Vf 1 plus x Vfg by Vf. Delta Pa is equal to 0, and delta Pz is equal to g sin theta L upon Vf 1 plus x Vfg by Vf, and by adding all these three, we get the total pressure drop. Now, let us consider some numerical examples. So, example 1 is the same as the example 1 considered previously for calculating pressure gradients using different models. So, now we will consider the same example for calculating pressure drop. Here we have taken the length of the tube as 5 centimeter. Earlier it was 10 centimeter. So, the earlier we were calculating the pressure gradient at z equal to 5 centimeter. Now, we have taken the length as 5 centimeter, and we want to calculate the pressure drop from the inlet to the outlet of the pipe. The other data is the same. Okay. So, the properties are same as before, and dx by dz is also the same as before. The outlet quality is 0.0221, and dVg by dP is the same as before. So, m square is negligible, and 1 minus m square is nearly equal to 1. So, we can use the expressions which we have discussed, which we have derived. Now, the mean viscosity is calculated using McAdams relation, and we get RETP equal to 1052 and it is laminar flow. So, we use the laminar flow friction factor which is 0.01521 and then substitute in the expression and we get delta Pf equal to 0.00793 kilopascal. Delta Pa, we substitute values in the expression and we get 0.374 kilopascal and delta Pz will be 0 because it is a horizontal pipe in this case. So, by adding these pressure drops we get the total pressure drop as 0.382 kilopascal. Now, example 2, you remember that in example 2 m square was not negligible. The effect of the compressibility of the vapor phase was not negligible. So, therefore, we will not consider that example. If we take that example, then we cannot neglect m square and then there will be 1 minus m square in the denominator for every pressure drop term and then we will have to integrate numerically. So, we will have to write a code and then do numerical integration. So, it cannot be solved by hand. So, therefore, we will not consider example 2, but we will consider example 3. So, in the example 3 all the data is as before except that the length of the pipe here is 1 meter and the outlet quality is 1%. The properties are same as before. Outlet quality XO is equal to 0.01 and dx by dz is equal to 0.01 per meter. So, dVg by dP is calculated and then m square is calculated which is much less than 1. So, therefore, 1 minus m square is approximately equal to 1 and we can use the expressions derived for the pressure drops. The mean viscosity is calculated and then the Reynolds number for the two phase flow is calculated which is 2.52 into 10 raised to 5. So, therefore, it is turbulent flow and then we use the Blasius relation to calculate the friction factor for turbulent flow in smooth pipe and we get 3.53 into 10 raised to minus 3 and then we substitute the values in the expression for delta Pf and we get 0.512 kilopascal. In delta Pa also we substitute the values and get 0.165 kilopascal and delta Pz after substituting the values and calculating we get 6.39 kilopascal. Then after adding these pressure drops we get the total pressure drop as 7.067 kilopascal. Okay. Now, let us see how to calculate two phase pressure drop using the separated flow model. The pressure gradient by separated flow model is given by this expression minus dP by dz is equal to 1 upon 1 minus m square in the bracket 2 FFO by d g square Vf phi FO square plus g square dx by dz V star plus rho g alpha plus rho f 1 minus alpha g sin theta. Here m square is an expression which represents the compressibility of the vapor phase and V star is a shorthand for an expression which is given here. So, if m square is much less than 1, then again we can consider 1 minus m square to be approximately equal to 1 and in case m square is not negligible, then we have to retain 1 minus m square in the denominator and in that case we will have to do numerical integration and we cannot derive any simple expressions. So, we will consider only the case where m square is negligible. Now, by neglecting m square we get minus dp by dz is equal to this expression which was in the bracket, and we identify the first term as the pressure gradient due to friction, the second term is pressure gradient due to acceleration, and the third term is the pressure gradient due to gravity. And by integrating these pressure gradients we will get the pressure drops. So, now consider pressure drop in an evaporator tube with saturated liquid at the inlet. The total pressure drop will be equal to delta Pf plus delta Pa plus delta Pz, and delta Pf is the integral of the frictional pressure gradient, and we substitute the expression and convert from dz to dx. So, we get integral 0 to xo 2 ffo by d g square Vf phi fo square dz by dx dx. Delta Pa is the integral of dp by dz A, and we substitute the expression. So, we get 0 to xo integral of g square V star dx. Then delta Pz is the integral of dp by dz, and after substituting the expression and converting to dx we get 0 to xo rho g alpha plus rho f 1 minus alpha g sin theta dz by dx dx. Now, we will make some assumptions so that we can do the integration analytically. So, we will assume FFO equal to constant over the length, and Vfg by Vf is equal to constant, and dx by dz is equal to constant, which is equal to xo upon L. So, most of the quantities will come out of the integration, and we are left with the integral of 0 to xo phi fo square dx, and dz by dx is equal to L upon xo, and then we define phi fo square bar, that is the average phi fo square, as 1 upon xo 0 to xo phi fo square dx. So, then we get delta P f is equal to 2 f fo L by d g square V f phi fo square bar. Delta P A is equal to g square integral 0 to xo V star dx, and the integral of V star dx upon V f is called R2. So, we get delta P A is equal to g square V f R2. The expression for R2 after integrating V star, we get this xo square upon alpha O Vg by Vf plus 1 minus xo whole square upon 1 minus alpha O minus 1. You can do this integration as C, check whether you get the same expression. Now, delta Pz, here we get g sin theta L upon xo integral 0 to xo rho g alpha plus rho f 1 minus alpha dx. So, this expression within the integral is actually an average density, a weighted average density, and we call it rho bar. This expression we are calling rho bar, and then the integral of rho bar over 0 to xo we are calling it as rho double bar. So, rho double bar is equal to rho f minus rho g upon xo integral of 0 to xo alpha dx, and then we call the average Voigt fraction as alpha bar equal to 1 upon xo 0 to xo alpha dx. So, rho double bar is equal to rho f minus in the bracket rho f minus rho g into alpha bar. So, if we can calculate this alpha bar, then we can calculate delta p z. So, finally, we have delta p is equal to delta p f plus delta p a plus delta p z, where delta p f is equal to 2 f f o L by d g square v f phi f o square bar, delta p a is equal to g square v f r 2, and delta p z is equal to g sin theta L rho double bar. And then by adding these three pressure drops, we get the total pressure drop delta p. Now, if we can find phi f o square bar, r 2 and rho double bar, then we should be able to find the pressure drop. So, with separated flow model, we will use the Martinelli and Nelson correlation and then evaluate these pressure drops. We have seen some graphs given by Martinelli and Nelson. They had given some more graphs. They had plotted this phi f o square bar. So, here we have pressure on the x axis, on the y axis we have phi f o square bar, and for knowing the pressure and the exit quality, we can find phi f o square bar from this figure. The scales are logarithmic, both scales are logarithmic, it is a log-log plot. Okay. So, we can find phi f o square bar from this graph and then substitute and get the frictional pressure drop delta p f. For delta p a, we need r 2. Martinelli and Nelson had plotted r 2 also. Here pressure is on the horizontal axis and r 2 is on the vertical axis, and for different pressures and different exit qualities, we can find r 2, and here also the scales are logarithmic, it is a log-log plot. Using this, we can find r 2 and substitute and get the acceleration pressure drop delta p a. Now, to calculate delta p z, we need rho double bar, and then to calculate rho double bar, we need alpha bar, the average Voigt fraction over the length, but there is no graph which directly gives alpha bar. So, we have to find alpha at different points at different locations on the pipe from the inlet to the outlet, and then integrate from inlet to the outlet. Okay, from x equal to 0 to x equal to xo, we have to integrate. So, as a simple approximation, we can take the average quality, which is the quality at the midpoint, and then find the Voigt fraction for that quality, and then assume that alpha bar is approximately equal to that quality, that Voigt fraction. Here the scale, one scale is logarithmic, the horizontal scale is logarithmic, and the vertical scale for alpha is linear. Now, let us consider pressure drop for two-phase flow in an adiabatic pipe. So, we assume FFO equal to constant, VFG by VF equal to constant, and since it is an adiabatic pipe and we are not considering higher order effects, therefore, X will also be equal to constant. So, everything comes out of the integral sign in the expression for delta Pf, and we are left with only integral 0 to L dz, and this is nothing but L. So, therefore, we get delta Pf equal to 2 FFO L by d g square Vf phi FO square, and phi FO square we can get from the graph given by Martinelli and Nelson. Delta Pa, because the dP by dz A is 0, so delta Pa will also be equal to 0. Delta Pz, here also everything comes out of the integral, and we have only 0 to L integral dz, which is equal to L. Therefore, delta Pz is equal to rho g alpha plus rho f 1 minus alpha g sin theta L. So, by finding alpha, we can find delta Pz, and alpha we can find from Martinelli and Nelson graphs. So, delta P is equal to delta Pf plus delta Pa plus delta Pz, where delta Pf is equal to 2 FFO L by d g square Vf phi FO square, delta Pa is equal to 0, and delta Pz is equal to rho g alpha plus rho f 1 minus alpha g sin theta L. So, phi FO square we can find from this Martinelli-Nelson graph. Here we have quality and phi FO square for different pressures, and there is a table also which gives the two-phase multiplier phi FO square for different pressures and different qualities. So, using this we can find delta Pf. Now, for delta Pz we need alpha, the white fraction, and that we can find from this graph. For any given pressure and given quality, we can find alpha from this graph, and then we can find delta Pz. Now, let us consider examples. In example 1, we have the same data as before, except that the length is 5 centimeter here, and the properties are the same as before. So, we get dx by dz and xo, and then dvg by dp, and then we find m square, which is negligible. REFO is equal to 707, so it is laminar flow, and FFO is equal to 0.0226. So, phi FO square bar we get from the Martinelli and Nelson graph for the given pressure and outlet quality. We know the pressure and the outlet quality, and then we get phi FO square approximately 5.2 from the graph, and for the same given pressure and given outlet quality we get R2 as approximately equal to 2. So, we substitute these values and get delta Pf equal to 0.0613 kilopascal, and delta Pa is equal to 0.0209 kilopascal. Delta Pz is equal to 0 because it is a horizontal pipe, and the total pressure drop delta P is calculated as 0.0822 kilopascal. Now, we will not consider example 2 because there m square is not negligible, and we will have to do numerical integration by writing a code. So, we will consider example 3. Here the data is same as before, except that the length is 1 meter and the outlet quality is 1%. So, xo is equal to 0.01 and dx by dz is equal to 0.01 per meter. Then dVg by dP is calculated, m square is calculated and it is very small. So, therefore, 1 minus m square can be taken as 1. ReFO is of the order of 10 raised to 5. So, it is turbulent flow, and then we use the Blasius correlation to calculate the friction factor FFO, and then we use the Martinelli and Nelson graphs, and for the given pressure and outlet quality we get phi FO square bar equal to 1.3 and R2 equal to 0.1, and alpha bar is roughly estimated as 0.05. So, this has been done by assuming that alpha bar is approximately equal to the alpha corresponding to the quality at the midpoint of the pipe. Rho double bar, using this alpha bar, it is calculated as 656 kg per meter cube, which is only slightly less than the density of the liquid rho f. So, after substituting these values, we get delta Pf equal to 0.671 kilopascal, delta Pa is equal to 0.145 kilopascal, and delta Pz is equal to 6.43 kilopascal. And then by adding these pressure drops, we get the total pressure drop delta P equal to 6.51 kilopascal. Now, consider the drift flux model, and let us see how two-phase pressure drop can be calculated using the drift flux model. So, using drift flux model, we calculate the frictional pressure gradient using the homogeneous model, and the expression for the acceleration pressure gradient and gravitational pressure gradient are the same as those for the separated flow model, but alpha here will be calculated by using the drift flux model. So, alpha is equal to Jg upon C0j plus Vgj, and then we substitute for J and Jg, and then we get this expression Gxvg upon C0 Gxvg plus G1 minus x Vf plus Vgj, and then we differentiate this with respect to x, keeping pressure constant, that means Vg and Vf are constant. So, we get deba alpha by deba x at constant pressure equal to alpha by x minus alpha square C0 Vfg upon xvg. V star expression is given here, and the expression of m square is also given here. These are the same as those for the separated flow model, and in case m square is much less than 1, we can neglect it and we can take 1 minus m square is approximately equal to 1. So, here we will assume that m square is negligible. So, we get the total pressure gradient as 2 ftp by d g square v bar plus g square dx by dz v star plus rho g alpha plus rho f 1 minus alpha g sin theta. Okay. So, now let us consider an evaporator tube in which the inlet is saturated liquid, and we will assume ftp equal to constant over the length of the pipe, Vfg by Vf is equal to constant, and dx by dz equal to constant equal to xo upon L. So, the total pressure gradient delta P is equal to delta Pf plus delta Pa plus delta Pz, and here delta Pf is the integral of the pressure gradient due to friction, and we get this expression, which is the same as that for the homogeneous model, 2 ftp L by d g square Vf 1 plus xo by 2 Vfg by Vf. And for the acceleration pressure drop, we integrate the acceleration pressure gradient and get g square Vf R2, and where R2 is equal to 1 by Vf 0 to xo V star dx integral. Delta Pz is the integral of dp by dz z, and this is equal to g sin theta L rho double bar, and this is the same as what we got for the separated flow model. So, the total pressure drop delta P is equal to 2 ftp L by d g square Vf 1 plus xo by 2 Vfg by Vf plus g square Vf R2 plus g sin theta rho double bar. So, now to calculate this pressure drop, we have to find R2. For that, we will have to find alpha, and we have to find rho double bar. For that also we have to find alpha. So, now consider an adiabatic pipe and assume ftp equal to constant, Vfg by Vf equal to constant, and x will be constant in this case. So, delta Pf will be equal to 2 ftp L by d g square Vf 1 plus x Vfg by Vf. Delta Pa will be 0 in this case, and delta Pz will be equal to rho g alpha plus rho f 1 minus alpha g sin theta L. And by adding these three, we get delta P equal to 2 ffo L by d g square Vf phi fo square. Actually, here we do not have to use phi fo square. So, instead of this expression, we will use this expression. Okay. And plus rho g alpha plus rho f 1 minus alpha g sin theta L. Now, let us consider some numerical examples. Example 1 is the same as before, except that the length of the pipe is 5 centimeter, and the property data is the same as before. Dx by dz is equal to 0.443 per meter, xo is equal to 0.0221, and dvg by dp is of the order of 10 raised to minus 5 SI units, and m square is of the order of 10 raised to minus 3. So, we can neglect it. The average viscosity is calculated using Macadam's relation, and RETP is 1052. So, it is laminar flow, and FTP is equal to 0.01521, and alpha O is calculated using the outlet quality, and using the outlet quality we calculate C0 and VGJ, and then after substituting these values of C0 and VGJ, we get alpha. So, we get the value of alpha O as 0.82, and then we calculate R2 by using this value of alpha O, and it turns out to be equal to 5.27, and then we substitute the values and get delta Pf equal to 0.00793 kilopascal, delta Pa is equal to 0.055 kilopascal, delta Pz is equal to 0. So, by adding these pressure drops, we get the total pressure drop as 0.0629 kilopascal. Now, as before, we will skip example 2 because m square is not negligible, and then we have to do numerical integration by writing a code. So, we will consider example 3. In this, the length is 1 meter and the outlet quality is 1%. The other data are the same as in example 3 we have considered before. The property data are the same. Outlet quality is 1% and dx by dz is 0.01 per meter. dvg by dp is calculated and m square is calculated, which is of the order of 10 raised to minus 5. So, it is negligible. So, 1 minus m square can be taken as 1. Then mu bar is calculated and RETP is calculated and it is turbulent flow. So, using Blasius correlation we get the friction factor, and alpha O we get from the expression for the drift flux model. We get the C0 and VGJ and substitute and then get alpha O corresponding to XO, which is 0.0908, and then we substitute it in R2 and we get R2 equal to 0.0916. Then after substituting the values we get delta PF equal to 0.512 kilopascal, delta PA is equal to 0.133 kilopascal, and alpha bar is the average alpha and that is equal to 0.0476, and this we have taken as the Voigt fraction corresponding to the average quality. Average quality is taken as the quality at the midpoint, which is half of the outlet quality, and corresponding to that the Voigt fraction alpha has been calculated using the drift flux model, and we get alpha bar equal to 0.0476. Then we substitute this alpha bar and get rho double bar equal to 658 kg per meter cube, and then by substituting it we get delta Pz equal to 6.49 kilopascal. So, the total pressure drop by adding these pressure drops we get 7.135 kilopascal. So, as I have mentioned before in the earlier numerical examples, that these examples are for the purpose of illustration only. Please check the calculations, there may be errors in the calculations. So, please do your own calculations and check. But the methodology I hope is clear, and using this methodology you should be able to calculate pressure drop with homogeneous model or separated flow model or drift flux model, whichever model you choose, and for a evaporator tube or condenser tube or adiabatic two-phase flow, for all these three types of cases you should be able to calculate pressure drop. If m square is negligible and if you make simplifying assumptions, then the expressions which we have derived by analytical integration can be used, and then you can calculate pressure drops by hand. Otherwise, if these simplifying assumptions cannot be made, then you will have to do numerical integration by writing a code. Thank you.